This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 2, Problem Type 1. So we'll go ahead and go into that game. And as always, it's very important to review the introductory tutorial for the game before beginning, which we'll assume you've done here, as that contains a lot of crucial information for completing the exercises. It's also a great idea to look at some examples at this level, and I strongly recommend doing that before you try to solve the problems yourself. For right now, I'm going to go ahead and go straight into a problem. Now in level 2, these problems are going to be a little bit more complicated, not just simple inverting or non-inverting amplifiers or voltage followers, but instead we're going to have a larger number of resistors. And I'll wait for that to go ahead and load here. Okay, so it's going to give us the instructions that we need to complete the exercise here, which you can always bring back up if you need to from the help menu. And we can observe that we have a circuit with one operational amplifier pointing to the right here, with the two inputs, the positive and negative input, and the one output, whose current is basically indeterminate. And we have over here what essentially, remember that these three different ground symbols, and for that matter the one that's connected schematically to the op amp, not directly but really via the positive and negative power supplies, which are not shown here. So all those points are actually connected together by invisible wires here. So that's a standard conventional electronics to use multiple ground symbols to avoid cluttering the diagram. And so we'll use that here. So the input really is kind of a voltage divider. If you think about it, that's a single loop there, and its output is going into one of the inputs here, which doesn't draw any current because remember, an ideal op amp has essentially an infinite impedance across the inputs, and then the output is connected to that of a voltage controlled voltage source whose control voltage is the difference between these two input voltages, as discussed in the introductory tutorial. So basically this is a voltage divider, and then we have what you might recognize here is actually a non-inverting amplifier because it has, first of all, proper feedback from the output to the negative input through a resistor, and the input voltage here is connected to the positive terminal. That's what tells us it's a non-inverting amplifier that'll have a positive gain as opposed to a negative gain. And actually the gain is just going to be 1 plus this resistance divided by this. And that's really a quick way of solving the problem. But I'm going to show the more detailed method right now. So we're going to go ahead and treat this as an ordinary nodal analysis, and with a slight modification for op amps. And remember that we virtually always do nodal analysis on op amps because the meshes are not really clear given the internal elements there, and it might even be non-planar. So we're going to do nodal analysis, and we also don't select our ground here as you would normally do because that's really the fixed ground of the power supplies, which we don't want to try to change. So we're going to just use the given ground, and first of all we'll have a voltage constraint equation as always because we have an independent voltage source here, or any voltage source for that matter. And so that's going to basically determine the value of V3 with respect to ground. So we'll just need one node voltage there, and that's going to be equal to a fixed value since this is an independent source. So that'll be the value of V3. And basically 0 minus V3 is 2 volts. So that means V3 is basically negative 2 volts. So we'll go ahead and check that equation. And that is correct. Then the second type of equation that we always need for op amp circuits is what we call the input constraint equation, which basically establishes the fact that due to the negative feedback and the very high gain of the op amp, it maintains its two inputs at the same voltage. Not any specific value, but just the same voltage. It's as if there's a virtual short here, except that that short between the inputs does not carry any current. As I said, there's no current into or out of each of these inputs. So basically that just says that V4 and V1 are the same. And you could write that equation various ways. Let's say maybe just V4 minus V1 is equal to 0 is one way of writing it, or any other algebraically equivalent way you can do. So we'll check that, and that is correct. And now we need to proceed to the core equations of a nodal analysis, which are, of course, Kirchhoff's current law equations, summing up the currents entering or exiting nodes, because we know those always sum to 0. So there's a total of 4 nodes in this circuit, V1 here, V2, V3, and V4 as they're numbered. And if we look at each of those in turn, well, V1 looks promising because it's not connected to any voltage source and it's not connected to the output of the op amp. Remember, that output of the op amp is internally the output of a voltage source. Therefore, we don't know the current coming out of the op amp. It's whatever it needs to be, and therefore we cannot write a KCL equation, for example, for node 2 because that's connected to that output of that voltage source. But node 1 is not, so that's perfectly fine. So we'll select that one. And basically, remembering that the current here into the negative input is exactly 0 in an ideal op amp. Real op amp, it might be on the order of picoamperes or something like that, but it's negligible for our purposes. And so we need to add the current, for example, leaving that node, say through the 3 ohm resistor, which goes to ground. And there's also a current leaving that node to through the 7 ohm resistor, which goes to the output of the op amp, which can and does source or sink current as required, again, as a voltage source does. So through the 3 ohm, we just have one node voltage involved, driving it to ground. And through the 7 ohm, there's a difference in node voltages involved, so we'll use that term. And then that's going to add up to 0 here. So I'm going to have V1 divided by 3 is the current going down here. And then the current going from V1 to V2 is going to be V1, of course, minus V2 divided by the corresponding resistance of 7 ohms. So I just fill that blank in, and we'll check that equation. And it is correct. Now, as we said, we cannot write a KCL equation for node 2, and if we try, it'll just give us an error, so I'm not going to do that. For node 3, well, once again, we have a red flag here because it's connected to a voltage source whose current we don't know. Voltage sources supply whatever current is needed by the circuit, and we can't really determine that without solving the rest of the circuit. So we will not do it for node 3, but we can do it for node 4. And node 3, of course, we already have a constraint equation, so we don't need the equation there. So for node 4, it's connected only to the input of an op amp, which has no current, and therefore no voltage sources are connected to node 4, so we should be fine there. Okay, so adding the currents that leave that node, there's really only 2, one going down through the 9 ohm, so we'll use that term here, 1 node voltage, and then the current going to the left through the 4 ohm, so that'll be a difference in node voltages divided by the resistance. And again, there is no current here because that's just the nature of an op amp, and so we don't have to include that term. We just set this equal to 0. Okay, so first of all, we'll have fill in the blanks, so that's just the V4 divided by the 9 ohms, and here it's going to be the V4 minus the V3, voltage difference driving the current to the left, and divided by the 4 ohms, and that will be our equation. So we'll check that, and that is correct. And if you think about it, that really is just a voltage divider equation written in a slightly different form. Okay, now we need to evaluate our SOT variables as well. So we have a SOT power that dissipated in the 9 ohm resistor, and so we're going to select SOT branch power because it's in one element or branch. And it reminds us that we do have several other palettes of terms we can use here if we click on those if we need them, but we won't need it here, so I'll just stick with the first palette. So the power dissipated in the 9 ohm is equal to basically 1 voltage minus the ground, so just basically V4 squared divided by the resistance. That's the standard formula for power in a resistor. We could put in a numerical value right away if you wanted to here using this term, but I'm just going to do it sort of the long way, if you will. So we'll put V4 squared divided by 9, and we'll check that. And of course that power should always be positive. I mean, you could put a minus sign out here, but you're guaranteed to be wrong unless you also put a minus sign over here. Okay, then we have the V20, which is the voltage of the op amp output with respect to ground, node 0 in other words. And so for that, that's called a SOT non-branch voltage because it involves a difference of two node voltages that are not connected by a single element. So the equation is very simple though, because it's just V2 minus V0 by definition, and so that's really just V2 since V0 is always 0. So we check that, and that is correct. So now we can count how many equations we have. We have 1, 2, 3, 4 node voltages to solve for, and nothing else, no control variables. So then we need 4 equations, and indeed we have 1, 2, 3, 4 equations of that type, and so that's sufficient to solve. So we're done basically doing that, and we have both of our SOT variable equations in addition. So we click no more equations now. And now we will have to sort of systematically simplify these equations if we want to do this again sort of the long way. And so here's the form to do that. So the first equation basically just says V3 is -2. So we'll multiply V3 times a 1 and then enter a -2 for the constant value, and that basically just expresses that equation. The next one says V4 minus V1 is equal to 0. So the V4 will have a coefficient of 1. The V1 will have a coefficient of -1. Or we could have switched which one is 1 and -1. It doesn't matter, but that'll be fine. And then for these two equations, this is going to involve a little bit of arithmetic here, so I've done that in advance. And so for the V1, basically, the third equation here, we have 1/3 plus 1/7 are the coefficients of V1. So just adding that up on a calculator, that's 0.4762. So we'll just put that in here. And the coefficient of V2 is -1/7, which is, and we could actually enter that as a fraction too, so I'll just go -1 divided by 7, and it'll automatically evaluate that for us as the -0.1429, which is probably familiar to you. Okay, then for the last equation, we have, for V4, we have 1/9 plus 1/4, and that, again, on a calculator is just 0.3611. Just 0.25 plus the 0.1111, which you can probably do in your head. And so that's the coefficient of the V4. So that's 0.3611. And then the coefficient of V3 is just -1/4. And again, I can put that in as a fraction if I want to, or I could just type the decimal of -0.25, but it does that automatically. So now we've entered all those equations, and that should be correct. So we'll go ahead and check that, and that is correct. And again, if you wanted to skip to the final answers, you can do that. Since I said there's easier ways to really solve this, but and now it does want us to form the matrix equation, although we surely will not use this to actually solve, not if we're trying to do it efficiently. So I'm just going to copy there using the copy button, which is fine, or we could enter them again, but there's no point. So we check that, and that's correct. Okay, so now it instructs us basically to not use a calculator or MATLAB to solve. And here, if we look at it, V3 is just -2. We know that one already, so we'll just put that in directly from this equation. V1 and V4 will be the same, but we need to solve for those. So let's start out by solving for V4. And so in order to do that, we can use this bottom equation that involves only it and V3, which we already know from this equation. And so I can just solve this sort of preliminarily for V4 by writing 0.3611 V4 is equal to plus 0.25, bring this term over to the right, plus 0.25 times the value of V3, which, as we know, is -2. And just that's -0.5, and then just dividing by this coefficient, V4 is -1.385. So we can go ahead and enter that there. And then I'll just copy and paste that into V1 as well, because we already know, I'll get the whole thing though, paste that here because it has the same value, because we know this equation says they're both the same. Okay, and then we just have to find V2. So now we'll use this equation that involves V1 and V2, and we just determined V1, so we can basically solve that for V2. So we just take the minus 0.1429 times V2, or actually just up here is probably easier, and then bring this term over to the right. So we have minus 0.4762 times V1, and we just determined that as the minus 1.385, put that in there, and then just do the arithmetic here, dividing by this, of course, and that gives us a minus 4.615. And again, whenever you're doing arithmetic like this, you'll probably do it on your calculator, but it's always good to just look at the numbers and see approximately what you should be getting to make sure that you didn't misplace a decimal point or hit the wrong button on your calculator. So make sure your number looks reasonable. And here we can kind of see that that does. This would be, that ratio looks quite reasonable for the number. Okay, so we'll put that in as negative 4.615. And that completes the solution. So now I'll just check that. And that is correct. And then the last step is to evaluate the sought variables. And I will point out before we do that actually that there would have been maybe an easier way to solve this back at the beginning. As I said, this is a voltage divider, if you recognize that, since this is just basically sensing that voltage. And so we could have just used a voltage divider formula. We could say V4 is simply the input, which is negative 2 volts, multiplied by the resistor of interest here, whose voltage we want, which is V4, divided by the sum of the two resistors in the voltage divider, so divided by 9 plus 4. And that's another way of getting V4 directly as just minus 1.385. Probably faster than going through all this equation writing in algebra. And then once you have that, then you could use the fact, if you remember, that the voltage gain of a non-inverting amplifier here is just 1 plus this resistance divided by this one, or 1 plus 7/3. And so we just take that, multiply by that input voltage now, and that gives us the answer quite directly without really doing all this business of writing equations and things. But it's all equivalent, so that's another way of doing it. Okay, so now for the sought variables, for the power dissipated in the 9 ohm, again, that's just V4 squared over 9, which I rewrote from our equation here. And then we just put in the value of V4, which was this 1.385, and square that, divide by 9, sign doesn't matter, and that's going to be 0.213 watts. And again, always check it to make sure it looks reasonable, but it does. And remember that the power dissipated in a resistor is always positive, right? It couldn't possibly be negative because of the nature of the formula. So if you're getting a negative value, then you know right away that that's incorrect. And the V20 is just the same as V2, which we already have, so that's the minus 4.615. Okay, so we'll check those values, and they are correct. And it's going to go ahead and it generated the transcript of the steps that we took, which you can use later in reviewing or studying. You get to that through the review work button. And you do have the option to view a detailed explanation if you like here, which would just show you how each of those equations is actually formed, and if you don't want to use the simple approach. But with experience, you might decide to use the simple approach, which is a little bit easier. In any case, it shows the currents here color-coded and the equation terms, and then you could look at the other KCL equation as well. And you can also get explanations of, for example, the op-amp input constraint equations, which maybe is less familiar to you. So here's just a discussion of op-amps and how they work, just a review of what's in the introductory tutorial, basically, and that might be useful. And of course, you can also pull up detailed explanations of other equations as well. And the Gaussian elimination, again, if you really want to solve the problem that way, it's probably the hardest way, but it would show you the steps for that if you like. So I'm going to go ahead and close that up. And this is where you would review the work if you want to look at your transcripts. So that concludes this problem.